What did y'all get for 3 to the 6th?
729.
729. So I could get my answer from this by doing 3 to the 6th, which is 729, and then multiplying that times 27, which is 3 to the 3rd, right? And whatever I get when I punch that in, somebody do that math for me. Get my calculator so I can check it. Well, 729 times 27.
19,683.
How much?
19,683.
19,683. Did everybody else get the same thing? Yep, okay, cool. So I could do it that way, and I would get the right answer. But I could also, before I do this stuff here, I could, because these have the same bases, because there's a 3 as the base for both of these problems, raised to some exponent, I can combine the exponents together. How would I combine the exponents together if the base is the same?
Add 6 and 3.
I would add 6 and 3, right? So the rule is if the base is the same, then I can think of this as 3 raised to the 6 plus 3. That's these two numbers here added together. All right, so that's our rule for exponents when you're multiplying two numbers together that are raised to an exponent that have the same base. Each term here has the same base. So 3 times 6, 3 raised to 6 plus 3 is the same as 3 raised to the 9th power. And if I punch that in my calculator, I should get the same number that I got here. So you guys see if you get the same number if you do 3 to the 9th. 19,683 is what I got. Same thing, right? But this is the simpler way to do it. I only had to punch one thing in my calculator at the end versus making sure that I didn't make a mistake when I raised this one to the 6th power and then raised this one to the 3rd power and then multiplied those together. So you guys should have seen that rule before. Do you remember that rule with exponents? So a lot of times, we tend to think about it. It's more common to see this when you have variables. So if I have x squared times x to the 5th power, and that's the same as x to the 2 plus 5, so x to the 7th would be what the end result is there. But we call that the product rule for exponents. When the base is the same, and by base I mean the number or the variable, right, that we're raising to some power. If the base is the same and those terms are multiplied together, then you can simply add the exponents. So if you have something like this, what would the answer for that be?
X to the 12th power.
She said x to the 12th, and she got that by saying it's x to the 2 plus 5 plus 3, all right, which is x to the 12th. So you just add those exponents together. Now notice that only works when these guys are all multiplied together, right? That would not work if we had x squared plus x to the 5th. We couldn't combine that any further. There's nothing more we could do with that particular problem. That's as simple as we could make it. All right, so the terms have to be multiplied together and have the same base in order for that to work. So let's try another one. What if we had x squared, y cubed, x to the 3rd, y to the 4th. How would I do that one?
You separate them into 2 categories and then add them.
So yeah, think about x's and y's. So we're going to put all of our x's by one another, x squared, x cubed, and then we're going to put our y's together. And I'm just going to put them in ascending order of the exponent. So I'm going to rewrite it like that. These are all multiplied together, so multiplication you can multiply in any order, right? So it's not a problem to sort of rearrange the terms when you write it down. So I'm going to group it like that so it's very clear to me which ones I'm combining together. And so since these have the same base, x squared times x to the 3rd power becomes what? X to the 5th, right? And somebody else, Ada's just rocking today. Somebody else want to give me what the y's would be?
Set y7 or
Y-
y8.
Y to the 8th, because there's an understood 1 here, right? Whenever you don't have an exponent, there's an understood 1. So this would be 1 plus 3 plus 4, so it'd be y to the 8th. All right? So that's another rule that we have to make sure that we remember. if we have a number 3, we can think of that number as 3 to the first power. Anything to the first power is itself, all right? So 3 to the first power is 3, y to the first power is y. What about 3 to the 0 power?
It'd just be 3.
That's 1. Anything to the 0 power is 1. So it's important that we remember that. In fact, I'm pretty sure that's important.
Wouldn't you just leave 3 by itself though?
Right here.
Yeah, because you're not multiplying it by anything, so wouldn't you just leave the 3? And
So the way that we think of 3 raised to the 0 power is we think of that as like 3 times 0. All right.
So why wouldn't the answer be 0?
Oh, I'm sorry. We don't think of it as 3 times 0. You're right. Why do we think of it as 3 to the 0 power is 1? That's a good question as to why we think about it this way. It's just a rule. Right? It's just one of those math rules you have to make sure you don't, because I can't remember. Do you know why?
No, but I'm about to wonder why. Can you change that rule?
You can't.
If someone happened to change that rule, could they?
They couldn't.
Because
It's locked in time and space forever. No, that's just the math rule. If you raise something to the 0 power, you get 1. Right? And you've got your calculators. You can always try that on your calculator to verify that. Right? If you ever forget the rule, if you raise anything to the 0 power, it's 1. And I just don't remember. I mean, it's one of those rules that I learned so long ago, and I've practiced for so long, I don't remember why you do that, like how to explain that to you. I just know that's the rule. All right? So anything to the 0 power will always be 1. This one makes sense, right? Because when you think about powers, right, what is 3 squared? 3 squared is 3 times 3. So it makes sense that 3 to the first power would just be 3. Right? 3 times nothing else. But why would 3 to the 0 power be 1? I can't reason that out of my mind. I just know that's the rule. So don't forget it. All right? Make sure you guys commit that to memory. For some reason, it must have been another class's test. Like I just put that on a test.
you put that on our test.
Was it on your test, your most recent one? Was it on the quiz you took today?
Mm-hmm.
Okay, all right. So had we taught, yes.
So you cannot simplify an addition problem with the powers?
So let's talk about when you can simplify an addition problem. So if you have x squared plus x cubed, you can't. All right? We can simplify this if it was x squared times x cubed, or we would write that as x squared, x cubed, just write them side by side. That implies multiplication. So this would be x to the 5th. But this we can't combine. However, if you have x squared plus x squared, we can simplify that. So that's another topic that we wanted to talk about today. Why can I simplify that, but I can't simplify this?
Because they're the same numbers.
Because they're the same numbers, which makes these terms like terms. When we learned about like terms, these terms have the same variable. Sounds like someone knocked, didn't it? These terms both have x squared as the variable. And so what do we do whenever they have the same variables? We add the coefficients together. What are the coefficients for each of these terms?
X.
No.
Or 2 and
There's an understood, huh? Did you say Cohen? Oh. What? What's the coefficient for x squared?
Understood 1.
There's an understood 1, right? So there's an understood 1 on both of these. So it's really 1x squared plus 1x squared. What's the rule when we have like terms? We add the coefficients together. So this would simplify to 2x squared. Okay? So our exponent rule that we're talking about, that only applies when they're multiplied together. But there is a way that you can simplify sometimes when there's exponents and there's addition or subtraction signs between it, and that's if the exponents are the same. You can add and subtract like terms together. Okay? All right. And that was actually our next topic. So just to make sure we're clear, let's do a problem that's a little more complicated. So let's say that we have x squared y p to the fifth plus 2xy squared p to the fifth plus 3 p to the fifth x squared y minus 7y squared x p to the fifth. All right, and we're told to simplify this. Now the first thing that I'm going to look at is I'm going to see, is there any simplification I can do within each term? Can I use the rules that we just learned and combine any of these combine any of these variables together, because we have multiple variables to different exponents that are the same variable. Are there any that we have that scenario?
You can do the x2. There's one in the front and like one close to the end. Do you see
So are you talking about this and this? This
Yeah.
and this? Yeah. Yeah, but that's like terms. That's not the scenario where you have something like that. So I was looking to see, do we have anything like that in any of our terms, right? How many terms do we have in this expression?
Oh, one. We have 3 or 4.
We have 4, right? The terms are divided by the pluses or the minuses. So we've got, these are our 4 terms. And so if I zero in on the individual terms, like if this term here, for example, had been y x squared y p to the fifth, we would want to simplify that first and make it y. Based on the rules that we just learned, whenever you have,
You combine two ones.
I can combine the two y's, right? They have the same base. They're both raised to an understood first power. And so I can rewrite this as, I'm going to write it in alphabetical order. So I can rewrite this as p to the fifth x squared, and now I'm going to combine the y to the first power and the y to the first power and make that y squared. Right? Do you guys understand that? We just added the exponents together because the y's, these parts of it have the same base. They both have a y as a base. So I'm allowed to do that based on what we were learning at the beginning of the lesson. Did I lose anybody with that? Yeah?
Do you have to put them in alphabetical order?
You don't have to, but this is why I'm doing it, okay? So here's what I want to point out. In each of these terms, we can't do this. There aren't any that have the same variable multiple times, so there's nothing else to simplify as far as that goes. So my recommendation for the next step is to put them in alphabetical order, and here's why. If you put them in alphabetical order, it will be a lot clearer when you have like terms. So all I'm doing now is I'm rewriting each of these with my numeric coefficient in the front and all of the variables put in alphabetical order. Now when I do that, it's very easy for me to see which ones have the same variables raised to the same exponents, right? So for this one, is there another one that's the same as this? This is what you were talking about before, right? This one has the same variables as this term does. Same variables raised to the same powers. So those are like terms. Does everybody see that? And then both of these, this one and this one, both have p to the fifth x y squared. So they have the same variables as well. So those are like terms. So those are the ones that I can combine. I can combine this one and this one. Like Cohen told us, this has an understood 1 in the front, so this is really 1 plus 3. So our final answer for these two is going to be 4p to the fifth x squared y. All we do is add the coefficients. And then here, since this one and this one are like terms, we have 2 minus 7, which is a negative 5. And then we just write down the variables. So that would be our final answer for this problem. You guys see the benefit of putting in alphabetical order so that it's clear, you can tell when they are indeed like terms? Joni, you look like you want to ask a question. What's your question?
You just forget about the other. I don't even know what to ask.
What do you think I forgot about?
Because there's 4.
Right? So I want to make sure you see this. Do you see that this term right here is this one? It's basically these two combined together. So I took these two here, I combined them into just that. Does that make sense to you? And then for this term, I took these two and combined them into that. And when I combine them together, that means that because they had the exact same variables that were raised to the exact same powers, I was able to just add their coefficients. I added a 1 and a 3 and got a 4. And I added a 2 and a -7 and got a -5 right here. Yes?
This is all yes, but I'm just checking. You do not add like the other p to the 5th powers. all
These things here,
together.
yeah, you don't add any of that stuff. Those are just part of the like term. When you find like terms and you're combining like terms, all you add is that numerical coefficient in the front. Okay? Is that clear to everybody? You want to ask your question a different way? Did that maybe help you understand how to ask the question better?
Yeah, I was gonna ask another thing. I often get confused with all the, what's the word for negative addition?
So like the pluses and the minuses and all this sort of
Yeah,
stuff.
when they're all lined up like
Right.
that, I get confused. Do I add this number all the way to here?
Yeah.
Or do I subtract this number all the way?
And that's why we identified the ones that were like terms. It was by identifying the like terms we understood this goes with this, and then this goes with this. And so it becomes a really simple, just 1 + 3 addition problem for this, and it becomes a really simple 2 - 7 additional problem for these terms. We just zero in on the coefficient, the number in the front, and that's the addition problem, or the subtraction problem that we're doing. Okay? All right, so that was chapter 21. Let's look at chapter 22. And 22 has to do with just making sure that we remember, first of all, making sure that we know what an equation is. Who can tell me what an equation is? What do we have to have in order for it to be an equation?
Symbols and numbers.
There's one symbol in particular. Think about the beginning of that word, equation. That sort of gives it away. An equal sign. An equation has to have an equal sign in it. All right? So this would be an equation because you've got an equal sign in it. All right? If you had this, we wouldn't call that an equation. We would call that an inequality. These are inequality symbols. This and x is greater than, less than or equal to that. Those are all inequalities. This is an equation. All right? This, right, what we were just working on just a minute ago, like if we had something like that, that would just be an expression. That's not an equation because there's no equal sign in it. Equations have to have equal signs in it. Okay? And so when we talk about algebra, we, and you guys should have done this in pre-algebra, we worked a lot with equations and rearranging the equations. And we're going to have more complicated equations in here. But we need to just kind of review the steps for dealing with really simple equations. All right? And the first thing that we need to recognize, though, about equations is that for it to be a true equation, whatever's on this side has to equal what's on the other side. Okay? So if we had an equation that was like this, that is an equation. That equation is true, right? Because it's true that 2 equals 2. All right? However, if I said this would be true, this would be a false equation. It's still an equation because it's one thing set equal to another thing, but it's not true because 3 does not equal 7. All right? Does that make sense to you guys? So sometimes we're going to, when we're trying to solve for a particular variable, we're going to plug it back in to the equation after we solve for that variable, and we're going to say, is it true if we plug that value back in? So we're going to do some practice with just plugging values into an equation. So if we have an equation like this, x squared equals -5x minus 6, and they ask us, does -2 or +5 satisfy this equation? All right? How are we going to determine that? Whether or not it satisfies the equation? Where we're going to plug that value in for x, and we're going to see if we get a true statement. All right? That's our goal. So we're going to start with the -2. So we plug it in, we say -2. I always like to use parentheses when I plug it in initially so that I don't get my signs mixed up or something. So -2 squared equals -5 times, wherever there's an x, I'm going to plug in a -2. Okay, so this is our first one. We're saying x equals -2. Let's see what we get when we do x equals -2. Did I lose anybody when I went from here, from this line to this line?
Yes.
I did? Okay, so all I did, we're checking to see what are we going to get when x equals -2. So everywhere there's an x in this equation, I put a -2 in there. Do you see that? I've got x squared here, so I did -2 squared here. I've got -5 times x here, so I did -5 times -2. So everywhere there's an x, I put -2. Okay, I'm just plugging that in. So now I'm going to simplify that. What's -2 squared?
It's +4.
+4, that's right. And then on this side, what's -5 times -2?
10.
It's +10, that's right. So 10 minus 6. So then I have 4 equals, what's 10 minus 6?
4.
4. So I have a true statement. You guys see that? So then we can say that -2 does satisfy the equation. All right? Now let's check our other value. Let's see if 5 satisfies the equation. So what if we say x equals 5? We're going to do exactly the same thing. We're going to take our equation here, and everywhere we have an x, we're going to plug in 5. So we say 5 squared equals -5 times 5 minus x. Everywhere there was an x in our original equation, I put 5 in there. Is that making sense now, Ada?
Yes.
Okay. Everybody else see that? So what is 5 squared? That's 25. What's -5 times 5?
-25.
-25 minus 6. And so 25 equals, what's -25 minus 6? That's -31, right? This is false. So 25 does not equal 31. That's false. And so this is not a solution. So our answer here would be that -2 is a solution. So you just plug the number in and see if you get a true statement. Now sometimes they won't ask it like that. They won't say, do these two numbers satisfy the equation? They may ask it like this. They may say, are these two numbers roots of this equation? And you need to understand that they're asking the exact same thing. When they say, are these roots of the equation, they're saying, are these numbers solutions for this equation? All right? And it is possible to have two different numbers that are actually solutions for the same equation. And I'm not going to go through it for time's sake, but if you look at example 22.2 in the book, for that equation, x squared minus 3x equals 10. If you plug in a -2 and a +5, both of those statements will be true. So in that case, you would say both of those are roots or solutions for that equation. Okay? All right, so these last two chapters, this should be super simple review. We've done this before, and it's just basically when you solve equations, you have to understand how to use the additive property of equality and the multiplicative, or is it the multiplication? Additive property and the multiplicative property of equality. And all that means is this. If we have an equation all right, if I have that equation there, and I told you to solve for x, what would your value for x be? Jonah?
3 plus 4.
3 plus 4. All right, that's exactly right. All right. Whether you realize it or not, what you just did is you used the additive property of equality. All right. Our rule with algebraic equations is that we're allowed to do anything to one side if we do that to the other side. Specifically in this case, we're allowed to add a number to one side as long as we add that number to the other side. So what you did in your head is you actually added a 3 to both sides. Right? If I add a 3 to both sides, this becomes 0. So I'm just left with x, and on this side here, I get a 7. Right? Some of you may have seen it, may have learned it like this. X minus 3 equals 4. You add a 3 to both sides, so you write it like this. And then when you combine it together, you just get x on this side, and you get 7 on this side. But we're allowed to do that And it doesn't change the value of the equation as long as whatever addition we do to one side, we do that addition to the other side, okay? So that's what the additive property of equality tells us, that we can add a number to one side as long as we add a number to the other side of the equation. Now when we say add, that includes subtraction, because really subtraction is just adding a negative number, all right? So I can also subtract a number from one side as long as I subtract it from the other side. So you guys have definitely done this before. This shouldn't be news to you. It's not something that I feel like we really need to spend a lot of time on. I just want to remind you of that. As long as you do it to both sides, then that's allowed. So if we have something like this, x plus 1/4 equals negative 3/8, the way I'm going to solve for x is do what? Trying to solve for x means I want to get x by itself on one side, so I've got to get rid of this 1/4. And so what I'm going to do
Subtract.
is subtract in this case. I'm going to subtract the 1/4 from both sides, right? So I'm left with x equals negative 3/8 minus 1/4. In this case here, I need to get a common denominator. That's negative 3/8. Over here is going to be minus 2/4. I'm sorry, 2/8. So my final answer for this one will be negative 5/8. That again is using the additive property of equality, okay? Now same thing, we do the same thing with the multiplicative property of equality, it's just we multiply on both sides by the same thing. So if we have something like this, let's see, x divided by 2 equals 4, I can solve for x here by multiplying both sides by a 2. If I multiply this side by a 2 and this side by a 2, what happens is our 2's cancel out. And so I've got x equals 8 would be the solution for that particular problem, right? I multiplied on one side, as long as I do it on the other side, that's allowed. Same thing applies with division, right? If we had 3x equals 9, I can divide this side by 3 as long as I also divide this side by 3. So I get, these 3's cancel out, and I get x equals 3 there. All right, this is not a news flash for anybody, right? You guys have seen this before, and so you should be able to swallow these problems down without any issue. Here's the one thing to remember. If I have something like this, let's do this. If I have 2/3 x equals, I don't know, 3/4. All right? How am I going to solve that? How am I going to use the multiplicative property of equality to solve this?
You're going to divide.
I can think of it as dividing both sides by 2/3, but since I'm dividing by a fraction, that's the same as doing what? Multiplying by the reciprocal, right? So I'm going to multiply both sides by my fraction flipped. 3/2. I take the 2/3 and I take the reciprocal of that. I did that to one side, so I have to do that to the other side, right? And so what I get, this cancels out, so I'm left with x here. And so 3 times 3 is 9, and 8 on the bottom. So that's how I would solve for x there, okay? Does that make sense? All right. You guys go to it. Have fun. Happy mathing. Like I said, let me know if you have questions. We can chat real quick now, or we can chat at lunch. I'm available.
I actually have a question. How do I access the videos? Or
Oh, they are, let me stop this.